Hello everyone, my name is Anudeep from third year BTech ECE, and my course project is NLPP used in signal amplification using KKT conditions. So let's see that. So signal amplification is either amplifying the amplitude of the signal, output signal with respect to the input signal, like amplifying y of t with respect to x of t. So this can be anything like we can amplify the power gain or the amplitude and transmit that output signal. So we can use nonlinear programming. Nonlinear programming is a type of programming in which the objective functions contain nonlinear elements like nonlinear variables x square, quadratic equations, or two variables, multiple variables, etc. So we have to take into account conditions or constraints such as noise, distortion, or power for solving nonlinear programming in signal amplification. One method is the Kurush-Kantakar method, which uses a Lagrangian constant to find the optimal solution of the required objective function. So the KKT conditions use a lambda value. Lambda is the Lagrangian multiplier to find the maximum value or minimum value or optimal value of the objective function while relaxing the constraints. So these are the practical applications of signal amplification using nonlinear methods. So in telecommunications or medical imaging or scientific research, signal amplification is used. Let's see the Kurush-Tucker method. Kurush-Tucker method is based on the Lagrangian multipliers to incorporate the constraints into the objective function. That means we are creating a Lagrangian function which uses the objective function and the multiplier and the constraints. So we define the objective function or a Lagrangian function by summing the objective function and multiplying with the lambda value with the constraint. There are certain necessary conditions that must be satisfied in the Kuhn-Tucker method, like complementary slackness and lambda is greater than or equal to 0, or lambda is less than or equal to 0, and the multiplication of lambda and the constraint is equal to 0. So this is particularly useful for solving nonlinear programming problems with inequality constraints. So let's consider an example of nonlinear programming. We need to maximize the power output of an amplifier. So let's assume that the power output of the amplifier for two input signals. We have two input signals. So for input signal 1, power output is P1 and it is E1 square. P2 is equal to G2 square. So total power output of the amplifier is P1 equal to P equal to P1 plus P2. We also have a set of inequality constraints like the total gain of the amplifier should not exceed the maximum value G. The total gain of the input signal must be non-negative. So these are the constraints. Total gain of the amplifier is less than or equal to G max, and the gains are always positive. So this is objective function P equal to P1 plus P2, maximizing the output power. So P1 equal to x1 square, P2 equal to x2 square. F of x is the objective function. Let the total gain of the amplifier be 3 dB. Hence, we can write x1 plus x2 as less than or equal to 3. This is the inequality constraint. So we define the Lagrangian function of x comma lambda as f of x minus lambda into h. This is the objective function. Lambda is the Lagrangian multiplier. This is the constraint. H is the constraint. So take partial derivatives with respect to x1 and x2. We get these equations, and this is the complementary slackness condition. Lambda into h equal to 0. We get this, and this is the constraint. This is the non-zero condition, and lambda is greater than or equal to 0 because we are maximizing the objective function in this case. So we can take two conditions from this: lambda equal to 0 or lambda equal to not equal to 0. In case lambda equal to 0, then we get these equations x1 equal to x2 equal to 0, and we can substitute in objective function. In case lambda is not equal to 0, we have to solve other two equations 1, 2, and 6 to get x1 and x2, and lambda equal to 3. So we have to substitute x1 and x2 in f of x to get this maximum value 4.5. Let's take a generalized example, another example. Suppose we have an amplifier with the input signal x of t and output signal y of t. We want to again maximize the power amplification. So with the certain constraints. So y of t is the output, x of t is the input. We can formulate as maximize p equal to integral of y of t whole square. This y of t whole square and this integral indicates the power of the output signal. We have to amplify this output signal power. These are the specific constraints like normalized input signal. So integral of x of t whole square equal to 1. For input signal normalization, this is to ensure that the input signal does not cross certain bounds, and this is the bandwidth constraint. That means the magnitude or absolute value of y of t is less than or equal to certain bandwidth, and the output signal power does not cross uh, p max. Y of t whole square is less than or equal to p max. This is the maximum power constraint. So we can write Lagrangian function as objective function plus lambda 1 into constraint 1 plus lambda 2 into constraint 2, lambda 3 into constraint 3. Lambda 1, lambda 2, lambda 3 are the Lagrangian multipliers. Take partial derivatives with respect to y. We do not need lambda 1 and lambda 2 and lambda 3 derivatives. We then we take complementary slackness conditions. That means this is equal to 0, this is equal to 0, this is equal to 0, and lambda is greater than or equal to 0. Um, and then we use this equation to solve for y of t, uh, and the variables x1 y of t and y of t whole square is the objective function. We put that y of t and y of t whole square in the objective function to get the optimal solution. So let's see the code. So here we are importing NumPy for mathematical computation, and CUIPy for optimization techniques, and traps function we are using importing traps from SCIPy library for integration. And so let's define the objective function. Objective function is the y square, integral of y square dx equal to dt, and the input normalization constraint, which is the x square equal to 1. This is the input normalization constraint. Here abs means absolute value. This is less than certain value, so epsilon, let's say constant epsilon. uh, let's define the bandwidth constraint, which means the output signal is less than certain bandwidth. This is the maximum power constraint. Power of the output signal should be less than maximum power. Let's define the Lagrangian function containing y lambda 1, lambda 2, lambda 3, and this is the objective function plus lambda 1 into constraint 1 plus lambda 2 into constraint 2 and lambda 3 into constraint 3. This is the objective function, Lagrangian function. So here we are defining the objective problem, optimization problem. So Lagrangian and Lagrange, this is a Lagrangian function. Let's take the initial guess for y naught. To solve for the optimal value of output signal, we are taking initial guess as y naught. So y naught, we can take certain values for y naught. So here are the constraint: equality constraint, inequality, inequality, three constraints. So can also set the bounds for output signal. So optimal value of output signal lies in these bounds. So the final result is the minimization of optimization problem. This optimization problem is this Lagrangian function, uh, and y naught is the initial guess. And here we are using method called sequential least square programming to find the next iterations, and bounds we are taking bounds into constraints, bounds into consideration, and the constraints into consideration. So we are printing the optimal value of y of t and value of objective function. So let's see the code, source code. So this is the source code that we have to run in compiler. So let's see. So this is, we are taking n equal number of steps 100, and this we are taking as the input signal, this which is the sinusoidal signal. X is a sinusoidal signal. um, this creates input signal x with 100 time steps, and the amplitude of signal is sinusoidal and varies between -1 comma 1. So this is the maximum power and minimum power. So let's define the objective function. Here we are taking minus because we want to minimize the objective function, which means maximizing the minus of the objective function. Objective function is y square, integral y square, and we are taking here power constraint. A is the uh, gradient of n by n identity matrix. Here np dot I creates a identity matrix of n by n columns and rows. Then gradient is taken, and this gradient is used in the power constraint to enforce the power constraint, and the p max and p minimum and a values. This is a linear constraint. So here optimization problem is defined. Why not initial guess is taken as -1 comma 1, and it is transformed into an array. into a column matrix minus 1 comma 1. These are the bounds in which the optimal solution lies. Here we have taken none. So result is the minimization of the optimization problem while taking in initial guesses, least squares programming, and bounds and constraints. So let's say, so this is the output y of t values, and this is the value of y of t integral y of t whole square. This is the value of objective function. These are the values of output variables, y values. We can take a number of steps as 10, bit 10 iterations, and this is the maximum value of the objective function. We can also take like 50 and then get the 50 values of y naught and the maximum optimal value of objective function. So this is it. Thank you.